There's a Passive House certified skylight at the top of the stairwell that sort of trickles light from the 3rd floor all the way down to the basement. And at night, there are high-powered LED lights cast into the slab below that illuminate the stair from below and has a sort of glowing effect with resin treads. So that's sort of the architectural expression of the stair, but it also serves as the return for our exhaust system, for our forced air system, because it's the one element of the house that really kind of continues from the basement where most of our mechanicals are located all the way up to the 3rd floor. So you must be wondering, what is the penalty that we're paying for a complex geometry, for something that has a pretty despicable surface to volume ratio? We asked ourselves the same thing. On the left, you can see the actual design, and we sort of simulated a similar, more compact, less overglazed design. And there was a slight decrease in heating, but the real savings is in the cooling reduction. And of course, it's the windows. One of the things that we went back and forth with the client on was that we were really downsizing their space. They were going from 10,000 square feet to 3,000 square feet. And there were some compromises that were made to sort of open up the space and bring in the outdoors and really treat the exterior and the outside of the home as sort of the 4th wall of the space, which is kind of what you can see from the living spaces on the front of the house. But that said, the details are still important to us. I had mentioned the sort of rain screen system that comes down over the exposed part of the basement. So we knew that we wanted to insulate the outside of the concrete so that we didn't have to sort of artificially fur out the wall condition. So this is where we started with our detail, knowing that this was going to be a weak point, and modeling that in Thurn sort of confirmed that. We went through a number of different ideas. What happens if we wrap the footing in foam glass, if we extend the foam glass down below grade? And the simplest solution was also the most cost-effective, which was just to add an interior stud wall and fill it with the mineral wool insulation we were using elsewhere. And the thermal bridge goes away. The nice thing about this detail is that it actually represented about 15% of our total energy, and so it's saving about $90 a year. Other details don't really have to do with energy use. This is the door in the basement at the walkout condition. And our first thought was, okay, well, maybe we can just create this concrete seat and wrap the foam glass, still keep it shy of the finished floor so that we can cover it with a slate threshold. But it ends up with a cold spot and the potential for condensation depending on the interior conditions. So what we arrived at was actually lowering the concrete at the door, wrapping the foam glass, which has about a 90 psi compressive strength, up and over the concrete, and then using another material to distribute the load, such as an AZEC or a fiber cement board, just to kind of stabilize the door on top of the foam glass. And the risk for condensation goes away, and the cold spot is sort of minimized. And this is the resulting detail that sort of addresses not only how it performs, but also what it looks like, how it sheds water out of the system. So I started by saying that we took on this challenge of insulation matter, and I think that's been reiterated today thus far about the problems of different types of insulation. And we've used our fair share of XPS and closed cell spray foam before, but this is David White's calculator showing basically the total environmental impact of a particular assembly as you increase the R value. We did consider a cellulose assembly for this project, but because we were allowed to measure the FAR to the outside of the sheathing. We couldn't really take that penalty that would have occurred from having to reduce the usable square footage by going to a double stud assembly, because it would have been further encroaching upon what we were allowed to build on the site. Interestingly enough, the mineral wool is pretty similar to that polyisocyanide. The two are actually on top of each other on this graph, but you can see that in stark contrast to XPS, which the more you use, the worse it is. A couple lessons learned. And thus far, the project is just being completed. We also like to test our homes before the windows go in. The large openings, particularly the curtain wall system, we really weren't able to do that. What was nice was that with the self-adhered with an air barrier, it was really easy to inspect visually to check for leaks and continuity from one system to another. But that was a little bit of a risk, not being able to kind of test the baseline house before all of the windows went in. We sort of pushed the limits of the tilt-turn windows, and I would probably make them about 6 inches or so less wide on the next project, just because of the stress that it was putting on the hinges and the air leakage that we got during our final testing. The curtain wall system that was used on the first floor was challenging to air seal. I think that we probably could have designed a better detail now that I've gone through the process once, but I wasn't particularly pleased with the system. We did get good feedback about the self-adhered air barrier, which was sort of a departure from our typical zip wall system. And the rigid mineral wood or wool does really need a thermally broken rain screen built into the budget, or something similar, like a blocking detail to resist the compression over time.